Hello everybody, this is a lecture on Introduction to Waves. Here's a few things we're going to cover. What is a wave? What are the different types of waves? What makes a wave? And are there certain behaviors that are attributable to waves? Although we'll cover that last bit in the next lecture. So, you've all seen waves on the ocean. You've all heard waves. You're hearing a sound wave right now. But a wave is just a disturbance that travels through a medium from one location to another. Here we have a diagram of a wave down here, or a GIF, a wave through some slinkies. The question is, do waves transport matter, energy, or both? Well, let's look at this diagram, or the GIF, I should say. We oscillate one end, and that oscillation travels all the way to the other end, but if we look at this little bit of the slinky, it doesn't really move much at all. When the wave travels, then it carries the energy, but it doesn't actually carry the matter with it. So waves transport energy from one place to another. Oops, let's go back one slide. We can have two types of wave shapes. We can have pulses versus periodic waves. If you take a jump rope and you quickly raise and lower one end, you'll see that pulse travel out, kind of like in this GIF right here. This is a representation of a wave pulse traveling along could be a string, it could be an electrical pulse that's traveling, but it's a pulse that's traveling. It's just one single disturbance that travels through a medium. Here, in these slinkies, we have another pulse. It's just a single disturbance that travels through a medium. A periodic wave is a wave where the disturbance repeats at regular, repeated intervals. So if instead of doing one bump, we oscillate at one end, we'll create this traditional wave shape right here where it goes up, down, up, down, up, down, up, down, and that wave will travel out. Periodic waves have a well-defined frequency, period, and wavelength. While pulses, you can't really measure that, but you still can measure how fast they move. Usually we classify waves based on some different characteristics that they share. So let's talk about some of the different types of waves. One, there's transverse waves versus longitudinal waves. This juxtaposition, this categorization classifies waves based on the direction of movement of the particles relative to the direction which the wave travels. Here, if I oscillate my slinky back and forth, left and right, the coils get compressed and stretched, but the wave travels to the right. This is a longitudinal wave. The motion of the particles is left-right, and the motion of the energy is to the right, so that's parallel. In a transverse wave, the motion of our particles is perpendicular to the motion of our wave. So if we oscillate our slinky up and down, we get this familiar up-down wave shape. Up, down, up, down, up, down. Even though the motion of our wave is to the left and to the right. It's called a transverse wave. Transverse meaning across, because our particles are moving across the plane or the vector of motion. So here's a representation here's a GIF of a transverse wave. We're oscillating the left side up and down. And we can see that our wave, that oscillation, that up-down motion, travels to the left and to the right. But if we look at any individual particle, it's just going up, down, up, down, up, down. We're transmitting energy but not matter. For transverse, particles are moving perpendicular to the direction of the wave. We can also diagram a transverse wave and label some important points. A crest is the highest point above the equilibrium position on a transverse wave. So that would be F and A. A trough is the lowest point, like the valleys. Crests are like the peaks, troughs are like the valleys. This dotted line represents the equilibrium position of our wave. And the wavelength, which is represented by the Greek letter lambda, it's a lambda, Greek L, is the distance between two adjacent similar points on a wave. So it could be the distance from crest to crest, that's lambda. It could be the distance from trough to trough, that's lambda. Or it could be the distance from equilibrium going up to the next equilibrium going up. That's also a, lambda. And the amplitude is the maximum displacement from equilibrium. So if we go from our equilibrium to a crest, that's our amplitude. Or if we go from our equilibrium to a trough, that's also going to be an amplitude. Longitudinal waves occur when our disturbance oscillation is parallel to the motion. So we oscillate our slinky to the right, and the wave travels to the right as well. So when we oscillate a slinky this way, we get parts that are compressed and parts that are stretched out. We call the compressed parts of a wave compressions. Pretty easy to remember. And the stretched out parts are called rarefactions. Here's, in this GIF below, we have a periodic longitudinal wave, or compression wave. You can see we oscillate the left or the right side left and right. The wave travels to the left. But the individual particles don't move very much at all. They just go back and forth, back and forth. Longitudinal waves also have a wavelength, just the distance from compression to compression, or rarefaction to rarefaction. They also have an amplitude, but it's harder to measure. It is still going to be our maximum displacement from equilibrium, but it's harder to see in just an image. Just talked about wavelengths, so I'll move on. Sound is an example of a longitudinal wave. This is a tuning fork oscillating, and those little dots represent the air molecules. You can see as we oscillate that tuning fork, the air gets compressed together, represented by those dark bands, and air molecules spread out from one another, represented by the lighter parts. So sound does involve basically air molecules bumping into each other, compressing and rarefacting. We can also classify waves based on mechanical versus non-mechanical. A mechanical wave is a wave that requires a medium through which to propagate and travel. It's just something made of matter. Our main non-mechanical wave is the electromagnetic waves, also known as light. Electromagnetic waves are generated by oscillating electric charges, and they don't require a medium to travel through, which means electromagnetic waves can travel in a vacuum. And a medium, this is an important vocab word, is just the matter that the wave travels through. Sound waves are mechanical, and they're longitudinal because they travel through a matter medium. The medium is air. This word propagate, we're going to use a lot for waves. When we say mechanical waves propagate through a deformable elastic medium, we mean they're generated in a medium and they travel through that medium. So here are a couple different types of mechanical waves. If you're ever at a sporting event and you do the wave where everybody stands up and it forms a wave around the stadium, that's mechanical, and the medium is the people. Water waves are longitudinal waves, or they're surface waves, depending on where you are. Surface wave is actually a combination of transverse and longitudinal. Actually, water molecules move around in little circles, but we'll worry about that later. But the medium is just the water. For seismic waves or earthquake waves, the medium is the earth. And for waves on a slinky or a string, the medium is just the slinky or the string. Electromagnetic waves, again, are non-mechanical. They can travel through a vacuum, and they come in several different types. They're classified based on how they interact with matter. We'll go more in depth with electromagnetic waves later, but you should know that different types of electromagnetic waves are radio, microwave, infrared, visible light, ultraviolet light, X-rays, and gamma rays. They're classified based on their wavelength, basically, and their wavelength also determines how they interact with matter. Frequency, we've already defined. The variable used for frequency is F, and the unit is hertz. 1 hertz is equal to 1 cycle per second, or for waves, 1 wave per second. This is valid for periodic waves. Okay, so what is the frequency of the little hand of a clock? Now we're talking about the smallest hand, which is actually the hour hand. So it takes 12 hours to go around, which means the frequency is once every 12 hours, or 1 for 12 hours. That should be in parentheses. The second hand takes 1 minute to go around, so frequency is once per minute. These are all in the wrong place. This should be up here. The Earth's rotation on its axis, how often does it spin around? Well, it spins around every 24 hours or every day. So it's once per day. Again, this should go up here. We've got some formatting errors. And the Earth's revolution around the sun goes around once a year. So once per year is our frequency. We could convert these to hertz if we wanted them to be in our SI unit, but we'll worry about that later. So frequency measures how quickly a wave oscillates, how many waves pass per second. I just want to point out that for a sound wave, the frequency is the same as the pitch. So a higher frequency is a higher pitch, and a lower frequency is a lower pitch. Sopranos will sing with a higher frequency note, while basses will sing with a lower frequency. This is a higher frequency. This is a lower frequency. Or a higher pitch. A lower pitch. Keep that in mind for sound. Period is the time it takes for one cycle to occur, or one oscillation to occur, or in our case, for one wave to pass. And we already know that period is 1 divided by the frequency, their reciprocals. So the period of the little hand of the clock, that's the hour hand, takes 12 hours. The period of the second hand is, well, the second hand goes around once every minute, so 1 minute. The period of the Earth's rotation is 1 day. And the Earth's revolution is 1 year. The SI unit for period is seconds, so we could convert all these to seconds, but it's not necessary right here. Waves also travel at a particular speed, which we can measure. So, let's say we stand on a dock and count that 20 waves pass by in 1 minute. If the wavelength of the waves is 1 meter, how fast are the waves going? Well, since waves are traveling at a constant speed, we can just use speed as distance over time. The total length of waves that passes is 20 times 1 meter, 20 meters, and it takes 1 minute. So our wave speed is just 20 meters per minute. Now this is a really important note about waves. The speed of a wave depends only upon the type of wave and the medium through which the wave travels. That means it doesn't matter how fast you oscillate a string, as long as it's the same tension string and the same string, that wave's always going to travel at the same speed. Wavelength doesn't affect it, frequency doesn't affect it. If we use speed as distance over time, we can think, hey, well, what's the distance of one wave over the time it takes for one wave to pass? Well, the distance for one wave is just the wavelength, and the time it takes for that wave is just the period. So speed is wavelength over period, and since period is inversely proportional to frequency, we could write it as speed is wavelength times frequency. That gives us our equation for wave speed. Speed is equal to wavelength times frequency, which we could also write as wavelength over period. But again, this is just another way of writing speed as distance over time. So let's do one example. An ocean wave causes buoys to oscillate up and down as it passes. The buoys oscillate once every 2.4 seconds. So once every 2.4 seconds, that's our frequency. Frequency is 1 every 2.4 seconds. If the distance between crests is measured to be 12.4 meters, how fast are the waves traveling? Well, distance from crest to crest, that's our wavelength, lambda, 12.4 meters. We want to find the speed, but we know speed is wavelength times frequency, so we can just plug in our wavelength, 12.4 meters, times our frequency, 1 over 2.4 seconds. Our speed then is equal to 12.4 over 2.4. 5.2 meters per second. Pretty easy. So in summary, a wave is a disturbance which propagates through a medium carrying energy but not matter. That is, as long as it's not an electromagnetic wave, it can travel in a vacuum. Waves can be pulses, single disturbances, or periodic, repeated disturbances. We can have transverse wave in which the molecules vibrate perpendicular to the motion, or longitudinal waves where they vibrate parallel to the motion. We can talk about the crests and troughs on a transverse wave, or the rarefactions and compressions on a longitudinal wave. And we can also measure the wavelength and amplitude of any type of wave. Mechanical waves travel through a medium, and electromagnetic waves can travel without a medium. And the wave speed v is constant in any particular medium. Our equation for wave speed is equal to wavelength times frequency. Hope that was helpful. Bye.